All right. All right, it's time to get going. Welcome back to everybody. Um, so I just moments ago sent an email to everybody. I don't know if you got it yet, but concerning the final project. Some people have been asking me about, um, are there any more, things we can do to raise up our grade? And ordinarily, I don't like doing that sort of thing. But the this is such a weird semester. And I've been feeling like it would be nice to have something else going on in this class other than our normal homework assignments and final exam, that I decided to make some kind of a final project. It's going to be optional because I don't feel good about creating big projects that everybody has to do when I didn't tell you about it beforehand. But I sent an email a few moments ago, and maybe I will just look through that. This is the assignment. I'm going to put this on the website too. Oops. This is what I wanted. The final project. So let's just look through this. You can look on your own. I sent in the email. It's a very open-ended assignment. Your job is to produce some kind of media representation of a concept that you learn in this course. You can choose any medium you want. For example, ordinary written essay, poem, story, etc. Podcast type audio, internet meme, images, or video. I want this to be kind of free for all. You can do whatever you want, really. Twitter thread, Instagram posts, TikTok, YouTube video. Some of these I don't even know how you would do. A Twitch stream. I put Tinder profile. That's mostly a joke, although I'm into it if you got something to show me. Quibi, that is entirely a joke. I know you can't make a Quibi. Quibi's over, isn't it? It's a stupid idea to begin with. These are all the kinds of things that I'm thinking about. And on the assignment, you can see I tried to make a cute meme here. I like the memes. I hope that you can all see this. This she's saying.
I missed what you said before. So we have like no physical exam. It's just this that's optional, or do we have physical exam plus this?
That's right. Yeah, I didn't mean to say that. I hope I didn't say that. You will have a final exam, like an ordinary exam. This is optional. It's going to be due at the time of the final exam, but it's not in place of the final exam. Sorry to get your hopes up. Anyway, it says what I want. You can do sort of like I said, whatever you want. I said you should demonstrate that you've thought deeply about one of the ideas from our class and are trying to express that idea appropriately in whatever medium you choose. So appropriately, I mean like, if you're doing some silly meme, then it should be silly. If you want to just like write an ordinary looking paper, that's fine too. Then it should be mostly serious or something. I said this is an individual project, so just do it yourself. Here's another meme I made. Take your favorite. I hope I didn't take all your favorite memes. Here's about the grading. Here's another one. That's a stupid one that I did. So it says this is optional. So it says you'll receive anywhere from 0 to 5 points, which will be added directly onto your overall semester average. So this kind of significant, I guess. I mean that'll basically bump you up a letter grade, like a plus minus on your overall grade if I like what you did. The grading is based on these two criteria. So you have to, my scrolling is messed up. Demonstrate that you've thought about and are communicating some idea from the course. Whatever you do should be representative of a creative effort, similar to writing an essay of a few pages. So like these memes that I made, I would say are probably not good enough just by themselves. So I said here, in that case, you might want to make several. One tweet or meme is not enough to earn much credit. And I say right there, if you're unsure if what you've done is good enough, then show it to me at a before the due date, and I'd be happy to tell you what I think. I said even if you are making memes or other kinds of jokes, they should indicate a depth of knowledge and understanding which is appropriate to our class. So like this here is an example of one that is cute, but not. I wouldn't give you much credit for this because all you're doing is like making a stupid joke about the word mean. Like this does not actually demonstrate that I understand anything about anything. It's just I know what the word mean means. It's not even the mathematical meaning of the word mean. It's the opposite of nice. So that is an example of sort of what not to do. Don't make some stupid joke that really has nothing to do with the mathematics. You should be actually communicating, demonstrating that you actually have thought about something and understand something. All right. The submission. This is just information about exactly how you can hand it in. It's due at the date and time of the final exam. You can send it to me by email, or if what you've made is appropriate to post on some social media or something, you can just post it somewhere and send me a link to it. If you do that, I said use a platform that I can get to through a website without making an account. I don't want to have to like download some special app just to look at what you did. And a little thing at the end there, if you make something cute, I hope you wouldn't mind if I show it to maybe the other professors or something. But if you don't want me to show it to anybody, that's fine. You can let me know, and I will not. All right. Are there any questions about that? I hope that. So my goal here is kind of to give you something sort of silly and fun to do because I appreciate fun and silly things from time to time. But also, I think it's a good opportunity for you to think about all the various, at times this class can feel like sort of a jumble of extremely technical things. And in a sense, it is. I mean, it is a collection of extremely technical things. But I hope that you take the time every so often to think about sort of like what does it all mean, or at least like how is this interesting, or what am I learning? Like what sort of big ideas am I learning that I haven't already known from my other classes or something? And I hope that this project gives you some opportunity to do that. Like those kinds of larger questions are not really convenient to ask on a homework or on an exam, but maybe a more open-ended thing like this will give you the chance to think about those kinds of questions. All right. Are there any questions about that or thoughts? Nope. Okay, great. I hope you like my stupid memes. I'm going to go back to my normal screen here. Okay. Great. Thank you for the chat. Somebody just chatted to me that they liked my stupid memes. Thank you. They didn't use that verbiage exactly. I appreciate it. Let's get down to business then. Back to what we were talking about last time, which was sequences of functions, convergence of sequences of functions. So at the very end, we were talking about this important definition of converging uniformly, right? We say Fn converges to F uniformly on some set A when, for all epsilon, I said this last time, for all epsilon greater than 0, there exists a big N, natural number, such that N greater than or equal to big N implies Fn of x minus f of x less than epsilon for all x in the set A. All right, this is the definition of uniform convergence of a sequence of functions. The difference between this and what we talked about before was pointwise convergence. The only difference really is right here, that this epsilon in the n, it must work, the n must work for every different point. The difference in pointwise convergence just says for each point the thing has to converge, but that means you might be using different n's at all the different points. But the definition of uniform convergence says the same n works for every point x. All right, that's the key difference between the two concepts. And we did one example here, which was, I'm not going to go through the whole example again, but oops, fn of x equals 1 over nx, right? This example, this fn of x converges, so this is an example from last time, converges to 0 uniformly on the set, not 0, 1 to infinity. And you can actually see this on the picture. I didn't really draw the graph of this last time, but or maybe I did. I didn't say much about the graph of this last time. The graph of this, from just looking from 1 to infinity, so I'm not going to try and draw the rest of it. Here's 0, right? That's the graph of 0, which I claim this is converging to. What do all the other graphs look like? They look like 1 over x, which begins sort of looking like this. I'm going to exaggerate the picture a little. And then 1 over 2x looks like this. 1 over 3x looks like this. 1 over 4x looks like this, and so on, right? And this converges uniformly. What that means is, it means there exists epsilon such that, I will say, eventually, all of the values are within epsilon of 0, right? 0 is the thing it's converging to. All values of f some big N of x are within epsilon of, not f of 0, I mean f of x, where in this example that I'm drawing here, the f is 0, all right? So it means, one way of thinking about it is, it means you can sort of make this little bracket of epsilons so that if you go down the sequence long enough, all the values are within epsilon of 0. At least all the values in my set 1 to infinity. So if you zoom in enough, and you will see that, you know, these functions, eventually, their values, all of them are inside this this little range there, that bracket of epsilons around the function that it's approaching, which is 0. All right. This is what uniform continuity, uniform convergence of a sequence of functions. It means that eventually all the values get close to the function that they're approaching. All right. Any thoughts about that? This is just what we did last time. I would like to, and last time we actually proved in this example that it was uniformly convergent, and it's actually not so hard to prove. It's just a more or less ordinary sort of epsilon and big N style proof. I would like to talk about some examples where it does not converge uniformly. So let's look through the other examples we discussed last time and just ask ourselves, we talked about pointwise convergence last time mostly. Let's just ask ourselves, for those examples, is it actually uniform or is it pointwise but not uniform? Let's check it out. So I would like to talk about, first of all, fn of x is x squared over n. This one, I drew pictures. You have the ordinary parabola, but then as you go down the sequence, they get sort of flattened out, right? And we demonstrated sort of earlier, last time, or the time before maybe, last time we showed that fn of x converges to f of x pointwise on, converges to, not f of x, I didn't say what f of x, 0, pointwise on all of R, right? If you look individually, point by point, say if I only focus right at this point, it is true that the values, when I plug them into the function, they will actually approach 0, right? And point by point, for every point individually, it is true that the values approach 0. My question is does it converge uniformly? Does fn go to 0 uniformly on R? This is actually a very different question. This means that thing about, you know, what I indicated on a picture before. Can you make like a little sort of bracket of epsilon around the resulting function, which in this case is 0, so that all the values are within epsilon? What do you think? Any thoughts about that? In this case, what it's approaching is 0. Is it possible to think of like a sort of move this over a little bit. For any small epsilon there, is it true that eventually, if you go down the list far enough, all the values of the function will be within that range here, this little bracket? So for n large enough, thank you for answering. Yeah, 50-50 chance. Are all values of fn of x close to 0? That's what I mean, right? Fn of x, of course, is x squared over n. Even if you took like n is 1,000,000, are all the values of that function close to 0? Somebody said yes before, but I seem to have ignored that answer. Any other thoughts? I think the answer here must be no. Because these are all parabolas, right? X squared over n, these are all parabolas. In fact, x squared over n is unbounded as a function, right? It is a parabola. It might be sort of smooshed down a lot, but the two ends of it still go out to infinity, right? No matter how big the n is, eventually the two ends of this function do go up forever for any n. Even if the n is 1,000,000, you know, you could plug in x equals 2,000,000. You get some big number for the answer here, right? So the answer, like I'm trying to convince you on an intuitive level to say, actually in this case, the convergence is not uniform. So here, fn of x, well, I'll just say fn does not converge uniformly to 0. Or anything else. It does not converge uniformly to 0 on all of R, all right? The way to think this through is just think about, is it really true that every one of these, eventually, if you go far enough, is it really true that the entire graph of the function lies inside a small epsilon neighborhood? And it does not in this example, because these graphs, they are all parabolas, and they all go unbounded upwards. All right. Can we prove this? Actually, this is another case in which writing the proof is not really hard. You just have to understand sort of what the definitions is. So here, Fn does not converge uniformly. Let me just write again what uniformly would mean. So uniform convergence would mean for all epsilon greater than 0, there exists n, natural number, such that n greater than or equal to n implies. Okay, here's where I'm going to start writing something specific to this question. Fn is x squared over n, right? Minus f, which is 0. And this is true for all x in R, right? This is what it would mean for this to converge uniformly, all right? so you have to ask yourself, is this really true? Now this looks like a lot of nonsense maybe, but this part, even if you just look at this part, this can't be true for all x in R, right? Because some of the x's are going to be super big, and this thing here will not be less than epsilon. So when x is large enough, x squared over n will be big, all right? And so there is no, even if the n is also big, there's always x's for which x squared over n will be very large, all right? If I wanted to say this a little bit more technically, I would say something like, no matter what n is, there are x with x squared over n, say, greater than 1, if you like. You know, it has to be greater than some specific number. It's not enough to say greater than 0, but you can say there's always x with x squared over n greater than 1. So that means x squared over n minus 0 less than epsilon for all x is impossible. Right? The definition of uniform convergence has all of this stuff attached to it, but really what you can focus on is just this part here, and you realize that this x squared, no matter what n is, the x squared is always going to be choices for the x squared which make it bigger than any epsilon you can think of. All right, so that's why that one does not converge uniformly. Any thoughts about that? Questions? All right, let's do another one. I got 2 more examples about this uniform versus not uniform convergence. How about, this is another one which we have discussed in the past few days. Fn of x is e to the power nx, and what this converges to is f of x is 0 if x less than 0, 1 if x equals 0. And we showed last time that Fn converges to f pointwise on minus infinity to 0. I don't know if you remember this example. This is about exponential functions, and they look like this, like that, right? And on the right side of the y-axis, they don't converge at all. And so I'm gonna ignore that side. I'm only talking about negative infinity to 0. And what they converge on the left side, what they converge to is this line and then that point right there. All right? Something crazy's going on with my computer. Okay? This is what we talked about last time. So this blue one is f. This blue one is f, and then these ones are, you know, f1, f2, etc. All right? They converge to that blue line together with that point. The thing that they converge to is not continuous, but they do converge to it all the same, because eventually these things, they get super flat and then they shoot up like that, right? All right. Again, I would like to ask, is the convergence uniform? In this case, what that means is, think about it in terms of this, you know, little epsilon. Is it true, if you look long enough in the sequence, that all the values can be within epsilon of the blue lines and this blue point? Is it true that all values are in sort of this bracket together with this bracket? Now the one up there around that special point is not really one that you need to focus on too hard. The one down there is more relevant in this case. What do you say? Is it true that all the function values eventually will be inside those brackets or not? You should be looking at the y values that come out of these functions, these red ones.
I would say it would be true.
All the values of these red functions are inside those two brackets. If you look at the ones that I drew so far, the values are not all inside the two brackets, right? Because, for example, this lowest red one has values up here, right, which are not caught by one of those two epsilon buckets. If I go further down the sequence, maybe they all end up inside. What do you think?
Won't there always be values between 0 and 1 when it goes up on the slope?
Yeah, I would say so. There will always be some values in this range, right? I mean, these functions, they are super close to 0 over here. I'll give you that. But they have to go up to 1 here. And so for all of these red lines here, they are always going to be sort of some points in this kind of no man's land in the middle there, all right? This should suggest to you that it is not uniformly convergent. That's because these points, they will not always lie inside these two regions, epsilon regions around the limiting function, the blue one. So can we try to write that down? This does not converge uniformly. So Fn does not converge uniformly on minus infinity to 0. Actually, the issue occurs right around here. If I was not including 0 in that interval, then they would converge uniformly. But since I'm including 0 here, that's where all the nonsense happens. Everything gets messed up when you consider points close to 0. Let's see. Can we try to explain that? I'm going to say sort of like what I said last time. I would say if it were uniform, what would that mean? That would mean for all epsilon greater than 0, there's this n greater than 0. Well, n natural number. Come on. Such that n greater than or equal to n implies e to the nx minus 0 less than epsilon. All right. For all x less than 0. Now I'm only considering the negative values because the value when it actually equals 0 is not so important because I don't really care about what happens up at that strange point. Really, I'm just thinking about these values sort of down there. All right. So what this means is this requires e to the nx. You don't have to write minus 0, and also the absolute values are not relevant here because e to any power is always positive. This requires this to be less than epsilon for all x less than 0. But this is just not true because e to the nx, it does not have to be super close to 0, right? It can be, like the lady said before. I didn't see who said it. It can be in this sort of intermediate range here. It can be greater than some epsilons. So this requires that for all x less than 0, but there are some small x with e to the nx, say, greater than a half. There are, like on this picture. No matter what the n is, there's always going to be some values that are far away from epsilon. They're, say, greater than a half. Am I off the screen? Sorry. Move it up. All right. So this one also is not uniformly converging. Any questions about that? I'm trying to give everybody like the basic idea of what uniform convergence means. It means all the functions eventually has to be within epsilon of the thing you say they're converging to. All the y values. In this case, they are not. All right. Let's just do one more of these, and then we'll maybe talk about something else. How about another? This is the last of the examples that we talked about last time. Fn of x equals sine of x over n. Actually, we did talk about this one. Maybe I'm gonna make it just mix it up a little bit. Let's do cosine instead of sine. How you like that? Cosine x over n. I'm getting crazy now. Cosine instead of sine. What does this look like? So cosine of x looks like that. That would be f1. Cosine of x over 2. Do you remember this example from last time? That the effect of putting x over 2 is to stretch this thing out in the horizontal direction. So that was cosine of x. Cosine of x over 2 would look something like, I'm going to see if I can get this right, something like this. Right? This red one is the second one. Cosine of x over 3, I'll draw in blue, something like that. You get the same general shape, only it's going to be increasingly stretched out to the right. All right? I'll draw a few more. Another red one. Ooh, that one went up first. I didn't mean that. And another blue one. How about this, right? This is what they look like. So can we talk first about what does this converge to point-wise, if anything? For point-wise, you just look, say, at a particular point. Let's say like this particular x value. What do the function values look like? There was this one, then this one, then this one, then this one. Do those values converge to anything? I don't know if it looks like anything on my picture. I tried to draw them in order. What do you think? Ooh, I got more colors. I can do a purple. Let's do a purple. That would be even flatter, right? The next one would be, get my pink on. The next one would be even more stretched out. What happens to these values as we keep on looking further down the list?
They converge to 1.
They converge to 1. Yes, thank you. This, cosine has a 1 here, right? So it seems to me that Fn converges to 1 pointwise. By 1 here, I mean, of course, the constant function, f of x equals 1, right? That is what it seems to me. At each individual point, well, there's something on my screen, sorry. That's my kid getting a text. At each individual point, I'm going to turn my moon is already on. Shouldn't that block my texts if I turn the moon on? I don't know. I thought I understood how the moon worked. Yeah, point-wise, at each individual point, eventually, if you go down the list far enough, the values will converge to 1. Is it uniform, though? Does Fn converge to 1 uniformly? I should say point-wise on R, right? This is true for all points, all real number points. Does it converge uniformly to 1 on R? That would mean that that picture got a little cumbersome. If I were to, well, here's one, here's another, here's another, Here's another. Converge uniformly means that you can put a little epsilon around here so that eventually all the y values of these functions will lie within the epsilon neighborhood. Is that true in this case? These functions, when you think about their graphs, eventually do you get so that the entire graph of the function lies inside that epsilon neighborhood?
No, because doesn't it still have to hit -1?
That's right. Yeah, the answer is no, because these graphs, they all look like cosine. They might be like super stretched out, but they're still eventually gonna go up and down from 1 to -1 and back to 1 again, right? These graphs, they all look like stretched versions of cosine, but they do not stay inside this this little neighborhood up here, even if you look far down. Like they will stay up here for a while, perhaps for a long while, but eventually all of these, every one of them is going to go down to -1 and back up to +1. So the answer again is this is not uniform because these functions do not all end up in that little neighborhood right there. All right, and to justify that, I would say uniform would mean, can I just sort of skip some of the other words that I was saying in these problems? Uniform would mean that cosine of x over n minus 1 is less than epsilon for all n in R, for all x, right? But that's not true because we know that, but cosine of x over n has the y value of -1 sometimes, right? Like you can say specifically when, like I guess when x equals pi times n. If you plug that in there, you get cosine of pi, which is -1. But cosine of x over n has y value -1 sometimes, and so that would mean that cosine of x over n minus 1 in absolute value is 2, which is certainly not smaller than epsilon. All right. I hope these pictures are making sense. Maybe not. Nobody's answering my questions right away, but maybe that's all right. I don't know. Any thoughts about that? Maybe you're wondering. I keep on saying no, it's not uniform every time. What would it look like if it really was uniform? I can try to make up an example. One where the convergence really is uniform. Well, actually, the first example we talked about was like that. F of x equals 1 over nx on the interval 1 to infinity. Like in this case, just looking starting from 1, this converges to 0 uniformly because all the graphs, my red is gone. I like that red. All the graphs look like this here. And in this case, it actually is true that eventually these graphs, they do lie completely within epsilon of where they're approaching, which is 0. The fact that these graphs are all of them, eventually the entire graph lies inside that, that bracket. So here, the convergence is uniform. But in those other examples, there were always like pieces of the graph which end up sticking outside of the epsilon region, which makes it not uniform. All right. Great. So it's a recurring theme, sort of big idea of functional analysis. This kind of stuff that we've been talking about is referred to as functional analysis. That is, we're doing like real analysis, but using functions instead of individual numbers every time in our sequences. A general theme is that sort of uniform convergence of functions is somehow better than pointwise. Better, I mean, in terms of the weirdness that can happen. If things converge pointwise, there's actually still opportunity for a lot of weird things to happen in the sequence. But if they converge uniformly, then things are much more controlled situation. There are better theorems you can prove when the convergence is uniform. So, for example, when let's say Fn approaches F uniformly, then actually we get lots of theorems that we're not really going to talk about. We're going to talk about one of these in detail, but you know, we're getting towards the end of the class. I want to give you some idea of what else you could talk about. We're just not going to get to it. We get lots of theorems. For example, if Fn is continuous for all n, then F is continuous. This is true only if the convergence is uniform, all right? If you don't put this uniformly, then what I just wrote is not true. If Fn is continuous for all n, then F will also be continuous. And the same, you can say similar things for instance, bounded. Then the F is bounded. When the convergence is uniform, then like the properties of the thing they converge to are similar to the properties that the individual functions had. So if they're all continuous, then the thing they converge to is also continuous. If they're all bounded, the thing they converge to is also bounded. Or unbounded also. If they're all unbounded, then the thing they converge to uniformly is unbounded. Or you could say differentiable. If they are all differentiable, then the thing they converge to is differentiable. This again is not automatically true for non-uniform convergence. Differentiable. All right. There's actually there's a little technicality. Actually, we need also the derivatives to converge uniformly. This is a technicality. I just don't want to say something false. We need Fn prime to converge uniformly. But if the derivatives also converge uniformly, then it is true the thing they converge to will be differentiable. And also you can say something about the integrals. We haven't talked at all about the integral in this class. Of course, there is a lot to say about the integral from a more sophisticated point of view than a typical calculus class. I thought maybe we're not going to talk about the integral. If you want to talk about the integral from the perspective of real analysis, then you can take our master's level real analysis class. We talk about the integral. I don't know if you're going to do that. You will learn about the integral. I thought we got 5 minutes left. Let's just look at one example which has to do with the integral. I think this is a fun example in my opinion. I want to let Fn of x be this. Check it out. I'm not going to tell you a formula for this function. I'm just going to draw the graph because the formula, it's not so hard, but there's no purpose in writing a formula really. It's a bunch of straight lines. It goes up like this, comes back down like this, and then it's 0 over here. All right, so this is the function where this point right here is 2 over n. This is 1 over n, and this of course is 0 over here. All right, this is what I want my function Fn to be. And this is a sequence, so for each n, you get a different function like this. All of these functions, they make this triangle, which goes up to a certain height, and then goes back down. All right? The height is n. So if I were to draw them all like in sequence, like the way that I usually do, the first one goes up to 1, right? And then comes back down. The second one goes up to 2, but it's half as narrow. That's because the the ending point here is also depends on n. The third one goes up to 3 and then comes back down. It's narrower still, all right? And so on. The next one goes up to 4 and comes back down even narrower, all right? Sorry, that picture doesn't look like much, but I hope you know what I'm drawing here. Each one makes a triangle. They go up to height n, and the distance across the bottom, I suppose, is 2 over n. So from the point of view of the integral, check it out. Here's something interesting. Do you notice anything about the area under the curve? That's what the integral represents. What would you say the area under the curve is? So here, I can write this as the integral. Let's just go 0 to 2, which 2 is like over here, right? So all of these triangles, they will be, their base width is narrower than 2. What do you say? What is this integral? Of course, it represents the area of the triangle, right? Try not to think of this as like an integral that you would do using antiderivatives. Think of it as an integral that you can do by finding the area of the triangle. This is a triangle. It's like the area would be 1/2 of the base times the height, right? What's the base of the triangle, the width at the base? Is anybody still with me? 2 over n, yeah. And the height of the triangle? N. You can see it on the picture, right? Here the base, 2 over n, and the height here is n. Okay, so what is this? This is 1. Every one of these triangles has area 1, right? So every time these triangles are getting taller and taller, but they're also getting narrower at the same time, and it works out so that their areas are always the same. The area is always 1. All right. What does this converge to, though? Can we think about that? We could think about just like point-wise. I'm going to maybe exaggerate the picture here a little, just so we can see. What if I look, say, at if I look just at this point, say, its first value is up here, and then here, and then here, but then actually after that its value goes down to 0. I think this function, if you look at any individual point, the values will eventually converge to 0. That's because these triangles, say at this blue point here, after the 4th triangle, the triangle is already past it to the left, and so all the remaining function values will be 0, right? And the same is true for any point. Even if you choose a point really close over here, it's still true that eventually those triangles will all move out to the left, and this point's values will be 0 forever. So in this case, Fn converges to 0 pointwise, right? This, it turns out, is not uniform. It's definitely not uniform. If you think about this little bracket of epsilons, those triangles will always stretch beyond the epsilon brackets. Although pointwise it does converge to 0. This is very strange. But what it means is the integrals, think about the integrals, right? The integral 0 to 2 Fn of x dx equals 1 for all n, but the integral of what they converge to, which is 0, of course, equals 0. All right. These graphs have area 1 every time, but the thing they converge to is area 0. This is very strange. So let me just say my last, this I'm not going to say any more about this, but this is another theorem about uniform convergence. If Fn converges to F uniformly, then any integral from a to b of Fn of x dx, those integrals are numbers, of course. They are the area under the curve. And so this actually makes a sequence of numbers, and what it converges to is the integral of f. You can see that that was not true in this example. In this example, we had 1 every time for the individual functions, but they converge to something with integral 0. It turns out, though, if they converge uniformly, then these integrals, their values, must converge to the value of this integral. That is, provided that the integrals exist at all. But I'm just assuming you can always find the integral of something. All right, I think that'll do for today. I hope everyone was following along. I don't know. Yeah, that's it for today. We got homework due tonight. Don't forget. Let me know if you have questions. I can try to help out by email. Otherwise, I'll see you on Friday.